In earlier junior high math, you probably learned about several kinds of transformations. You did those transformations with various shapes. So, for example, as a reminder, if we make a shape, we can do a number of things to it. There's four main kinds of transformations that you learned about previously. The first one is the simple one called a translation, where we just move a shape. We can move it left, right, up, or down. Let me pick that, and then we're going to move it, say, over here. So translation is just sliding a shape from place to place, and that's it. You also learned about reflections. So if I reflect this shape over the y-axis right here, it's going to make a new shape over here in quadrant 1. I could also reflect this shape around the x-axis, and now it would be a new shape in quadrant 3. So those are reflections of our original shape. You also learned about rotations. So rotations take a shape and a center somewhere, I guess I'm going to pick this center, and rotates it by a certain angle around that point that you pick as the center. You've probably only used the origin as the center of rotation. And then finally, you learned about dilations, where we make a shape bigger or smaller. I should make a point at the origin. So dilations, if we take this shape and dilate it about the origin and make it 0.25 as big, so 1/4 of the size, we get a smaller shape and it moves closer to that center of dilation. So that's all well and good, and what we want to do here is talk about how we can apply some of those concepts to algebra. So instead of transforming shapes and individual points, we're going to be transforming functions. We're starting off by transforming linear functions, but you can transform any kind of function that you want, not just linear. So let's take a look at this line here. So this is a segment of a line, and I've constrained it so that it's f of x equals x, but I've given it a limited domain from -3 to +5. That way we can see the effects that we're going to have on these. Before we do, let's go and look at some ideas behind these transformations. So we're going to focus on just 3 of the types, and we're actually going to change one of them a little bit. But let's start with what was always the easiest one, which is a translation. So translation, you may remember from earlier math, turns an xy coordinate into an x plus something, right? So let's say we're translating by 2 right and 3 up. So we have some numbers to work with. So it would turn xy into x plus 2, comma, y plus 3, because positive is to the right and positive is up. So we add 2 to the x and we add 2 to the y, and then that turns a point into a new point. And when we're talking about transforming or translating a function, we're doing the same exact thing. We're taking every single point on the graph and we're translating it by a given amount. So looking at my line here, remember that this line is just made up of infinitely many points all right next to each other. So if you took every one of those points and moved them to the right and up, then we would end up with a line that moves around. So I'll explain how we get this in a minute, but let's say we have 2 to the right, and, or was it 3 right and 2 up? I already forgot. 2 right and 3 up. So if I look at any point on the red line, so let's pick this left end point. It was at -3, -3. So if I moved it 2 right and 3 up, it should now be at -1, 0. And that point is right here at -1, 0. My previous y-intercept was 0, 0. If I move 2 right and 3 up, it should be at 2, 3, and that's this point right here that has moved right and up. So every single infinite point along this line segment has moved up and become the blue one. So that's kind of what we're talking about with translations, is the idea of we're moving the points, but we want to write what we're doing to the function, like to f of x. All right, so let's go back here. Translations are moving a shape. Then we had reflections. So reflections mirror a shape. And just like we did in earlier math, we can reflect over the x-axis or over the y-axis. We could also say across that axis. So we're mirroring all of our points. So every single point gets mirrored. And over the x-axis was xy becomes. Since we're going over the x-axis, it switches all the y values. So on our graph, if I had a shape over here, I'm mirroring it over the x-axis first, so the horizontal one. It's going to end up down here in quadrant 3. So all of my y values that used to be positive are now negative. So I end up with x comma negative y. Over the y-axis is the other way. So I'm switching my x values from negative to positive, and my shape ends up over here. So that one would be xy becomes negative x comma y. So hopefully all that's kind of familiar, and that's not really the way we're looking at it here, but it is related. So it's the same idea, it's just presented a different way. So I wanted to start off with reminders about how that works. We're not going to deal with rotations because rotations affect every point differently. So we're not going to be able to just add or subtract or change a sign like that. So we're not going to really deal with rotations. Instead, we're going to deal with dilations, but we're going to break it apart. So normally we're used to dilations having to change x and y by the same amount, and we end up with a similar shape. Instead of that, we're going to change this, and instead of dilations, we're going to be dealing with stretches. So a stretch is a dilation that doesn't necessarily act the same on x and y. So if I stretched this horizontally, it would stay the same height and get wider. So it's like when you have a picture and you grab the side of it. So let's see if I can make this a picture and pick it. So if I pick this and I grab it from the corner, I'm dilating it. I'm making it bigger or smaller proportionally so that everything stays similar. But if I stretch the shape, it's like grabbing it over here and making it wider or narrower or taller or shorter. So stretches are like dilations, but they're not maintaining similarity. They're only stretching in one direction or the other. So going back to what we learned before, dilations turned our xy coordinates into kx, ky, where k is our scale factor. So this one with stretches, we're going to be able to turn xy, if we're doing a horizontal stretch, it would turn it into kx comma y, or a vertical stretch would turn it into k comma, or x, I don't know why I put k, would turn it into x comma ky. So the things we're talking about here for function transformations are the horizontal and vertical stretches, the translations, horizontal and vertical, and the reflections. So in total, there are 6 types of transformations that we can perform on functions at this point. So hopefully that ties it back to something you remember. Now let's go take a look at this graph in Desmos and see how we can visualize these things. So we have our line segment, and I want to go one by one through the changes we just talked about. In order to transform a function, we make a new function, in this case g of x, and we apply some change to the original f of x. The easiest to think about is moving the graph up or down. So if I say add 4 to f of x, it just simply takes every point on the graph and moves it up 4 spaces. So very much what you would expect from what we just talked about. The one that's a little strange, though, is if we want to move left and right. So intuitively, we think if I put f of x plus 4, my graph should shift to the right because adding to x is positive. It goes to the right. The thing is, if you think of this as y equals something, the 4 is like on the same side as the x. So I think of it as like how equations have to stay balanced. Since the 4 is on the same side, we have to do the opposite in order to keep things balanced. It's just kind of weird, and it's a thing that no matter how much you think about, never really necessarily makes sense like the geometric version does. So this version just makes really good sense. This version is kind of confusing, and we have to remember that when we add something to x, we're going left, and when we subtract, we're going right. So horizontal changes in functions are backwards and weird. So plus 4 would move us to the left, whereas minus 4 would move to the right. So that makes the blue line go to the right. Let's look at reflections next. If I make f of x, remember f of x is my outputs. So if I make all of my output values negative, that's like making y negative, it's going to flip everything around the x-axis. So that's the exact same one we talked about here, where we reflected over the x-axis and the y values became negative. So literally we just said make all the y values the opposite, so my line flipped over the x-axis. If I wanted to flip it over the y-axis, you might have guessed that I'm going to make the x values negative. So I'm going to put the negative inside the parentheses with the x, and it's going to flip the other way. So now my mirror line is the y-axis. And then finally, the last kind of change we can make is stretching. So you might think stretching is like changing a slope of a line. So if we put, say, 3f of x, then notice, I'm going to have to zoom out, the overall width of the line stayed the same, right? The left edge of this red line and the right edge of the line is the same, but this line got taller. So 3 times f of x created a vertical stretch, whereas if I put let's actually look, if I make a vertical compression, so I do the opposite by doing a fraction, if I put 1/2, again, the width stays the same, but the height gets shorter. And then the last thing is a horizontal stretch or compression. Just like the translations were backwards, so are the compressions and stretches. So if I do 3 times f of x, you would think that the x values would get bigger. But when I put 3f of x, we notice that the x values get smaller. So this point that used to be at 2, 2, the x value is now 2/3 instead of 2. So we made it 1/3 as wide as it used to be. If we wanted it to be wider, we would do a horizontal stretch in which we put a fraction, so like 1/2. And now, again, we're the same height as the red line, but our line got wider. All of the x values got multiplied by 2. So both the horizontal stretch and the horizontal translation are kind of backwards feeling. They seem like the opposite of what you would expect. So in geometric terms, it makes a lot more sense going point by point, but for a function, we just have to remember that horizontal is kind of weird because at the end of the day, we're defining y equals something. So everything is about y, so the stuff that's about x gets kind of reversed. So that's a quick overview of what we're doing here and the 6 kinds of transformations we're doing. In a different video, we'll go into the details about each of these 6 and how it works exactly.